All right, shall I share my screen?
Yes, please. Let's make sure that it works.
Okay, hopefully you can see this.
Okay, so our last talk for the morning session is William Kretschmer, hopefully.
Kretschmer, yes.
Talking about quantum pseudorandomness and classical complexity. Please.
All right, thank you for the introduction. So I guess I'm going to start by sort of summarizing this work and explaining the relevant background. And to summarize this work in one slide, the main objects I'm going to be talking about are something called pseudorandom quantum states, which I'll usually abbreviate as PRSs. And intuitively, what these are, I guess, computational approximations to the Haar measure. And what that means is that these are states that look like Haar random states to any computationally bounded adversary. I'll give you a more formal definition later in the talk, but this is mostly what the talk is going to be about. And I guess the question that I try to answer in this work and in this talk is this very kind of deliberately broad question, which is, where do pseudorandom states fit into the complexity theoretic landscape? So how do they relate to complexity classes and other cryptographic primitives? And I guess what I'm going to try to do for the rest of this introduction is first tell you why you should care about pseudorandom states. I'm going to tell you a little bit about what we know in regards to this question, and then I'm finally going to try to explain why the answers we have to this question are kind of unsatisfactory, and perhaps even raise more questions than the answer. And so that's what I'm going to do in the introduction. That'll bring me right into the results. And I think with that, I'm going to get started. Although maybe before I proceed, one thing I will mention is that for this talk, I'm just going to be talking about pseudorandom states, but actually for this work, almost everything that I prove in this work also applies to a stronger object called pseudorandom unitaries. So I figured I would just mention that, but otherwise I'm not going to mention pseudorandom unitaries again in this talk. Okay, so first off, so why should you care about pseudorandom states? Well, I'd say there's probably three main obvious applications of pseudorandom states, and perhaps the most obvious one is cryptography. So pseudorandom states, these are a cryptographic primitive, hence we expect that you can use them for cryptographic protocols. And indeed, I think, well, there's one example we know, which is that you can use pseudorandom states to construct quantum money schemes, but there's very likely other applications that we just don't know about. A second natural application of pseudorandom states is in physical simulation or physical computation. Say you're taking some average over Haar random states or generic looking states. Maybe you're doing some computation involving thermalization. And there, well, you can use information theoretic approximations to Haar random states, but these can potentially be computationally expensive to prepare. And in that case, pseudorandom states can in some cases potentially be cheaper, I guess, for some of these applications. And finally, there's what I think is maybe the most exciting application of pseudorandom states. This is a connection to black hole physics that was recently established by Boland, Pfefferman, and Vazirani, and they showed that essentially any possible resolution to some very big questions in black hole physics have to be answered using some language involving complexity theoretic pseudorandomness, and in particular, something in the ADS-CFT correspondence. So I think no matter which way you look at it, whether you're a cryptographer, a complexity theorist, or a physicist, pseudorandom states are something that we have good motivations to want to understand. So with that, I'm going to finally give you the formal definition of pseudorandom states, and it's here. So an ensemble of states, which is keyed by, say, the n-bit strings, is pseudorandom if the following two properties hold. One, it should be possible to efficiently generate copies of these states given one of these keys. And two, there's a sort of computational indistinguishability criterion, which says that to any polynomial time quantum adversary, the advantage that this adversary has in distinguishing copies of this pseudorandom state from copies of a Haar random state is at most negligible in the security parameter. if you're a cryptographer, this definition should look very familiar because this is very similar to the definition of pseudorandom generators. And in fact, there's really only two key differences, right? One is that instead of being an approximation to the uniform distribution, these are approximations to Haar random states. And the other is that we allow the adversary to have multiple copies. So any polynomial number of copies of this quantum state, and this is motivated by the no cloning principle, where having many copies of a quantum state is potentially more useful than just a single copy. One thing I should also mention is if you've heard of T designs, these are not the same as T designs, and there's two crucial differences. One is that for T designs, this T here, this parameter, the number of copies, this is fixed in advance. Whereas for pseudorandom states, we require security against all polynomially bounded T, so you can't fix this T in advance. But the other key difference is that T designs are an information theoretic notion of approximation to the Haar measure. So rather than just considering polynomial time adversaries, T designs require security against essentially any possible adversary or any quantum measurement, basically. Okay, so this is what pseudorandom states are. So with that, so what do we know about pseudorandom states? Well, in the same paper in which the pseudorandom states were defined in 2018, it was shown that if quantum secure one-way functions exist, then pseudorandom states also exist. And I think for many people, this is fairly convincing evidence that pseudorandom states exist. One-way functions, we usually think of these as a mini crypt primitive. These are in line with pseudorandom functions, pseudorandom generators, and the assumptions we need to construct one-way functions are generally much weaker than the assumptions we need to construct, say, public key cryptography or indistinguishability obfuscation. So I think for most people, this is sufficient evidence to be convinced that pseudorandom states exist. So this is something we know, but what's sort of more poorly understood is, in some sense, the other direction. So assuming pseudorandom states exist, then what else must be true? Are there other cryptographic primitives or complexity theoretic implications of the existence of pseudorandom states? And in fact, this was even raised as an explicit open problem in this paper. In 2018, they asked, is there a converse to this theorem? So assuming pseudorandom states exist, does this imply that one-way functions must exist? So what I'm going to do next is sort of show you an example of a problem where we can sort of show that assuming pseudorandom states exist, this problem must be hard, but at the same time, we sort of can't really show this. And I'm going to explain what I mean. And what I'm going to do is I'm going to show that in some sense, a QMA protocol, so a quantum Merlin-Arthur protocol, can break pseudorandom states. So QMA, as we know, this is the class of problems that are decided by, well, as I said, a QMA protocol. This is sometimes described as being like the quantum analog of NP. And what this means is that these are things that can be decided by, there's always two players. There's Arthur, who is this computationally bounded and skeptical verifier, and Merlin, who is this all-powerful magical wizard who's potentially untrustworthy. And Merlin's goal is to basically convince Arthur by sending him some quantum state, let's say, that the input satisfies some property. And so what I'm going to show is that a QMA protocol can break PRSs, and hence, in some sense, if pseudorandom states exist, then it must be hard for polynomial time quantum algorithms to decide this kind of QMA problem. And the input, the problem just goes like this. So suppose Arthur has copies of this state psi, which is either pseudorandom or Haar random. So here's what Merlin can do. Merlin can send Arthur a description of some quantum circuit C, and Merlin basically claims that if you apply this circuit C to the all-zero state, you will get back a state that is close to psi. And this is something that Arthur can verify. Since Arthur has many copies of this state, you can use even just the swap test, let's say, to generate a bunch of copies and see if they match up. And so why does this work? Well, if psi is drawn from the pseudorandom ensemble, then we know by nature of the efficient generating algorithm of the pseudorandom ensemble that there must exist a short quantum circuit that produces that state. So in that case, Merlin can always pass this test. On the other hand, if psi is a hard random state, it's not hard to show by essentially just a counting argument that actually no polynomial size quantum circuit can even approximate psi to reasonable error. And so in that case, Merlin can basically pass this test with essentially negligible probability. So in that sense, like I said, we've shown that there's this QMA problem, which must be hard if you believe that secure pseudorandom states exist. But okay, I said there was sort of an issue with this construction. So what is that? Well, the problem with this is that while this is like a quantum Merlin-Arthur protocol, this is not actually defining a QMA language, right? So complexity classes like NP, QMA, BQP, these are defined in terms of, like I said, languages, which are subsets of n-bit strings. So the input, we always think of the input as being some classical input, but here the input to this problem, this copies of psi, is somehow inherently a quantum state. It's not a string. And so it's actually not really clear at all whether one can reduce breaking pseudorandom states to an actual QMA decision problem. And this was actually my original motivation for this work, was I kind of realized, something weird is going on here. It's not clear if you can reduce this problem of breaking pseudorandom states to any classical decision problem, actually. And so I was basically wondering, is this just a conceptual issue? Is there maybe a more clever reduction you can construct that would allow you to break pseudorandom states if you could decide QMA problems? So this was sort of my motivation for the work. And is there a question in the chat?
There's a comment. It says that instead of using the swap test, you could just run C inverse with psi. This is from Ronald.
Right. Well, okay, yeah, I guess you could do that. Yeah, maybe that's even more trivial. I guess you just have to repeat it enough times to get your confidence to be sufficiently high. But yeah, I guess that should work. Yeah, maybe the swap test is overkill. Okay, so that's essentially all the background I want to say. This actually brings me straight into the first result of this work, which shows that in some sense, this is not just a conceptual misunderstanding. There's actually something weird going on here. So what do I do? Well, I can show that there exists an oracle, a quantum oracle, such that the following two properties hold. One, BQP equals QMA relative to this oracle O. And two, pseudorandom states exist relative to this oracle O. So this immediately implies that, polynomial time quantum algorithms can decide QMA problems. And so somehow we know that this must be useless for breaking pseudorandom states because secure pseudorandom states exist relative to this oracle. But in some sense, this is saying something even stronger, which is, in my view, rather surprising. Because what this is basically showing is a black box separation between pseudorandom states and essentially all other interesting cryptographic primitives. So why is this? Well, in general, essentially all interesting classical cryptography can be broken if P equals NP, right? And okay, BQP equals QMA is almost like P equals NP, right? NP is contained in QMA. So this basically implies that relative to this oracle, we can decide NP problems in polynomial time on a quantum device. And hence, there can't be any secure cryptography, or at least any classical cryptography that is secure against quantum devices. And yet, there can nevertheless be these pseudorandom states which are secure against quantum devices. So this was, I found this to be very surprising. But I guess that's what we can show. But okay, so this also sort of raises this natural question of, well, if QMA is not enough power to break pseudorandom states, then what is enough power? Like what suffices? Can we place any upper bound on how much power you need to break pseudorandom states? And that brings me to the second result, where we can show that if you can solve sharp p-complete problems, so if BQP equals PP, then pseudorandom states do not exist. And moreover, this even holds relative to all oracles. So this gives sort of a nice upper bound on how much power you need to make pseudorandom states. So these are sort of the two main results of this work. With that in hand, I'm going to now discuss a few interesting applications of these results. And the first thing I'm going to talk about is an application relating to a task called shadow tomography. So this was defined by Scott Aronson in 2018. So imagine you're given a list of binary observables, let's say O1 up to OM, and you're also given a bunch of copies of some n-qubit state rho. And your goal is, given these copies, to estimate each of these observables, the expectation of each of these observables on the state rho, up to additive error epsilon, simultaneously for each of these. Now, what's interesting about shadow tomography is that Aronson showed that you can actually use this using surprisingly few copies of this quantum state. So the number of copies you need is just polynomial in the number of qubits, logarithmic in the number of observables, and also polynomial in this error parameter epsilon. And so in some sense, this says that with a polynomial number of samples, you can actually simultaneously estimate an exponential number of different observables. So this is quite powerful. One thing that was sort of left open, though, is are there any interesting cases in which this shadow tomography procedure can be made time efficient? Meaning, let's say with time scaling that's like comparable to the sample complexity. Well, unfortunately, there's sort of a trivial no answer to this. And this is just because the inputs and outputs to this problem are way too big, right? If you're given a list of m different observables, that's already m inputs, so you can't hope to get logarithmic scaling. Those observables, if they're given to you explicitly, they're also way too big in terms of n, because these would be like 2 to the n by 2 to the n size density matrices. So, well, and of course, also there's m possible outputs that you have to list, because you have to list all of these estimates simultaneously. So as defined, you can't hope to make this computationally efficient, but you can you can change the problem slightly to make it so that it's at least possible for this to be computationally efficient. So this was something that Aronson also defined, which is hyper-efficient shadow tomography. And in this slight variation of the problem, it's essentially the same task, but now the algorithm is allowed to operate implicitly on both the inputs and the outputs, rather than explicitly. So now, instead of being given this observable as like an explicit density matrix, the algorithm just gets oracle access. So we have some oracle that takes an index and performs the ith observable. You're still given copies of the state, but now the output also gets to be sort of implicit. So rather than listing all of the outputs explicitly, the algorithm is allowed to basically return a succinct description of the list of outputs in the form of some quantum circuit, C. So it outputs a description of a quantum circuit such that when you apply C to I, you get back the ith observable, the estimate of this observable on the state. So this is at least, now it's at least conceivably possible that in some interesting cases, one could have an algorithm here that scales polynomially in n and also in the logarithm of the number of measurements. Unfortunately, though, Aronson also showed that it's actually impossible to do this efficiently if you're only given oracle access to these observables. So if you only get black box access, then you cannot hope to do this efficiently, meaning in time, like I said, polynomial in n, log m, and epsilon. So we could hope to, I guess, relax this model even further. And that's what I'm going to consider next. So now let's consider a special case of this, where rather than being given general observables, now all of the observables are just going to estimate fidelities with some pure state psi. And now, rather than just being able to measure this observable, you're going to get even stronger access. You actually get the ability to produce copies of psi. This, you can show that this also lets you measure psi, of course. So this is sort of strictly more powerful. And there are even, I believe, some examples of query complexity separations where the ability to produce a state can be potentially exponentially more powerful than the ability to measure in a basis containing that state. So this should be strictly easier than what's on the previous slide. And I guess the question here is this possible? Well, what I could show is that actually even this task remains impossible to do efficiently, once again, assuming you just have black box access to copies of these states. And there's sort of a cute one-line proof of this. This is just actually a simple corollary of our first result, which is that, well, suppose otherwise, that we did have an efficient algorithm for this hyper-efficient shadow tomography with state preparation, then there would actually be a black box QMA reduction to break pseudorandom states. But of course, this is what our first theorem rules out. And what's sort of the proof of this? Well, here, these psi i's, you should think of these as being like the different states in the pseudorandom ensemble. The state rho is the state which is either some copies of a pseudorandom state or copies of a Har-random state. And here, this output circuit, this is basically what you would feed into a QMA algorithm, because you'd basically be asking, is there some I such that C of I reports something close to 1? Because in that case, then you've identified that one of these states, psi I, is close to rho. So that's the proof. So we can show that even the stronger form of, or I guess weaker, depending on how you look at it, form of shadow tomography remains impossible. Okay, finally, I have just one more application of our results, and this is something involving Har-random oracles. So here, well, sometimes something that we often do in classical complexity theory is consider complexity classes with a classical random oracle, but you can also consider sort of a quantum random oracle. So what this means is that, say, for each n-bit string x, we choose some unitary transformation use of x over n qubits. So this is in dimension 2 to the power of n. And an algorithm basically gets to query use of x, so you feed in x and it performs this operation use of x. You can consider complexity classes that have the ability to query this oracle. What we can show is the following. So if you can separate BQP from QMA relative to this Har-random oracle, then you can actually separate BQP from QMA in the unrelativized world. So in some sense, what this is saying is that this Har-random oracle is sort of, I guess in some sense, useless for proving oracle separations. Because if you could prove like a query complexity separation between BQP and QMA, then you would actually separate them in the unrelativized world. And this is in like stark contrast to classical random oracle, where we can actually prove unconditionally that BQP is not equal to QMA relative to a classical random oracle. So in some sense, what this is saying is that classical and quantum random oracles behave very differently. I think I should also mention that depending on how you define query access, I think you could even make this actually an if and only if. But I think for the purposes of this work, though, this is just the sort of the interesting direction of the implication. Okay, so with that, are there any questions? Because otherwise, I'm basically just going to jump into talking a little bit about some of the proof techniques in this work.
With that last result, can you replace BQP with QCMA or? How general is this?
It definitely generalizes. You might be able to replace it with QCMA. I'm not certain. Yeah, that's a good question. But yeah, I mean, I know you can definitely say the same thing about whatever. If you replace this QMA with like whatever quantum statistical zero knowledge or like some of these other interactive proof complexity classes, I think the same thing holds.
Are you going to explain how you prove this, or?
Well, okay, yeah, I'll actually explain a little bit on this next slide. But well, yeah, we'll see. So actually, so as I mentioned, so this first result that we proved, it's this oracle O relative to which one, pseudorandom states exist, but two, BQP equals QMA relative to this oracle. And this oracle O is actually extremely simple to describe. It consists of two parts. One is this random unitary oracle that I described on the previous slide, and two is basically any p-space complete language. Okay, so why does this work? Well, in some sense, what we could show is that a QMA algorithm cannot learn any non-trivial property of this random oracle O. And this turns out to follow from the extremely strong concentration of measured properties that are exhibited by random unitary transformations. And hence, when you're considering QMA relative to this oracle, we might as well basically just cross out this unitary part, this U, and we're basically just left with QMA to the P, so QMA to the P space, which by standard complexity theory is just equal to P space. And so this is how you show that BQP equals QMA relative to this oracle. Because basically all you can decide is just P-space complete languages. Okay, so what's even simpler, I guess, is showing that pseudorandom states exist relative to this oracle. This turns out to just be a simple application of the BBBV theorem, so the lower bound, quantum lower bound for unstructured search. And this works just because, well, query complexity doesn't care about computational efficiency. So giving this P-space oracle does not help you at all to break the search problem corresponding to deciding whether a state is random or pseudorandom. So this is essentially all that goes into the first main result. For our second result, showing that pseudorandom states do not exist if BQP can decide Sharpie complete problems, is sort of two main ingredients that go into this. One is a classical shadows protocol. So this is actually a form of shadow tomography. This was introduced by these authors in 2020. And the other is the famous post-selection theorem. So showing that post-BQP equals PP, which was proved in 2005. And so how do we use these together? Well, what this classical shadows protocol does, it essentially shows that in some sense, pseudorandom states can be information theoretically broken by an efficient protocol. There's just some efficient measurements you can perform such that once you've taken these measurements of the state, there's just some purely classical post-processing you have to do to determine whether that state is pseudorandom or random. And indeed, the measurements are really simple. They're just like, you take random Clifford measurements, basically. But this classical post-processing is potentially hard. What we show is that nevertheless, using some clever tricks involving post-selection, at least for the special case of distinguishing pseudorandom states from random states, you can do this classical post-processing efficiently if you can solve problems in post-BQP. So that's essentially everything I wanted to say about the results. I think with that, I'm just going to leave you with a few open problems, and then I'll take questions at the end. So kind of the first and most obvious open problem, I think, is can you prove something like this instead of with a quantum oracle, with a classical oracle? I think this is just a nice question. We have, similar questions where, say, we have an oracle separation between QCMA and QMA. This was proved by Aronson and Cooperberg in 2007, I think. And it also remains open whether you can prove that oracle separation with a classical oracle. And somehow it seems that like very similar issues seem to come up here in the same sorts of constructions. So I'd be very interested to know if you can do this with a classical oracle. I think another interesting question is whether you can give other evidence for the existence of pseudorandom states. So, another way of looking at what this work does is showing that perhaps it might be possible to base the existence of pseudorandom states on weaker assumptions than we usually think of as being assumptions for cryptography, right? And I'm basically wondering, can you instantiate this with some interesting and non-trivial assumption that's like also plausible. And then finally, I think another direction that would be interesting to look at is what's called quantum meta-complexity. So this means what is the complexity of problems that themselves encode complexity? So to give you an example, what if I ask, how hard is the following problem? I give you copies of a quantum state, and then I ask you, given those copies, to determine the size of the smallest quantum circuit that approximately produces that state. How hard is this task? Well, if pseudorandom states exist, then this should be hard, because it should not be possible to distinguish low complexity states from random states. But that's basically all we know about this problem. And I'd be interested to know what else we can say about this problem, especially because lately, a lot of the really interesting breakthroughs in classical complexity theory have involved looking at a problem through a sort of meta-complexity lens. And I'd be very interested to know which of these techniques can be ported to a quantum setting involving quantum states. So with that, that's about everything I had to say. So I'd be happy to take questions. There's even I guess I have a bonus slide if no one has any questions, but otherwise, I'm happy to hear what you have to say.
Thank you very much for the wonderful talk. Let's see if there's any questions. All right, we got one.
Yeah, so for the impossibility results for the hyper-efficient shadow tomography, so these are oracle impossibility results. Is there a reason, like, would it be plausible to try to prove a non-oracle, like impossibility result for a non-oracle version of it? Or is that run into like circuit lower bounds or something?
Oh, interesting. I'm not sure. Yeah, at first I was just going to say, yeah, maybe like, okay, assuming, well, okay, you would certainly probably need some computational assumption, but, whether you can prove something that using an assumption, okay, maybe just like assuming pseudorandom states exist, for instance. I'm not sure. It's a good question.
Thanks.
Yeah, so earlier, there was also this question about how do we, prove this results using random oracles, and so that's what I saved for, I guess, the last slide. This is kind of technical, which is why I saved it for the end, because I don't know if I'll be able to explain it well, but basically the key lemma we use is this concentration of measure property for the Haar measure. So if you have some function that is Lipschitz continuous and it's defined on copies of Haar random unitaries, then what this shows is that the probability that this function deviates substantially from its average by more than x, let's say, is actually exponentially small in the dimension of the Haar random state, or well, I guess the Haar random unitary transformation. So to give you some idea of what these parameters are, well, so n here, this is like 2 to the power of little n, where n is the number of qubits. This f of u, this is basically the acceptance probability of some QMA algorithm. So what does this mean? So here, Arthur, this is some quantum algorithm A, and here Merlin feeds Arthur some witness state psi, and Merlin is basically taking a maximum over all possible witness state psi over the probability that Arthur accepts. And finally, T is basically the number of queries that Arthur makes to this unitary transformation. So if we think of T as being like polynomial in little n, let's say X is like constant, like 1/3, and this big N is 2 to little n, then this is basically saying that the probability, if you choose a Haar random matrix, that this deviates substantially from the average is is not just exponentially small in little n, it's actually like doubly exponentially small in little n. And this is sort of the key property of the hard measure that we're using to prove these oracle separations and to prove that basically a hard random oracle is useless to a QMA algorithm, just because, well, like I said, the probability that this deviates is like doubly exponentially small, but there's only like singly exponentially many different QMA algorithms, essentially. So are there any other questions? Anurag asks, is there any reason why there's no dependence on K? Actually, this is just the interesting part of this. There's no dependence on K whatsoever. And this is sort of in contrast to, I guess if these were like a discrete random variable, there would like have to be some dependence on K, the number of copies. But yeah, there's actually no dependence on K, which is kind of interesting. I should mention, I did not prove this lemma. This is, you can find this in like a textbook about concentration of measure.
Let's take our speaker again. We have a little break before the afternoon session, I guess late morning session. Yeah, so we'll resume in about a half hour. Thank you.